If the universe were looking back at you, would it truly exist? Or could everything you have ever touched, seen, and trusted be nothing more than an exquisitely crafted performance? Like moonlight trembling on the surface of a lake, convincing yet impossible to grasp, scientists are now raising a chilling possibility that the universe itself may be a hoax of perception. Leave a comment with your thoughts, because this journey is not only questioning the universe, it is questioning our own existence. And from here, we step directly into the first question. What is reality, and does it truly exist? What if the most unsettling discovery in modern physics is not hiding in a distant galaxy, but sitting quietly behind your own eyes? You can reach out and touch the table beside you. It answers with certainty, firm, unquestioning. You tap your phone. You feel the glass resist your fingertip. You hear the small click of reality confirming itself. And yet, the deeper we look, the more that certainty begins to soften, as if the universe were a mirage that learns your habits and then performs them back to you. Albert Einstein once admitted, "Reality is merely an illusion, albeit a very persistent one." It is a line often quoted for poetry. But inside the laboratory, it lands with a strange gravity, because physics keeps returning to the same quiet warning. The world does not behave like a solid stage that exists whether you show up or not. It behaves more like a conversation, a relationship, a response to questions asked in a particular way. We begin with the assumption we carry through daily life like a lantern, that the universe is out there and you are in here, that the stars burn in silence whether anyone looks up or not, that mountains do not need witnesses to be mountains. It feels obvious because the nervous system is designed to make it feel obvious. But neuroscience and physics whisper the same caution in different accents. What you experience is not the world itself. It is a model of the world, a living sketch assembled from electrical signals, stitched into a scene by a brain whose first responsibility is survival. Donald Hoffman expressed this bluntly. We see reality through a species-specific interface. And evolution favors usefulness more often than accuracy. Imagine two creatures walking through the same forest. One sees the world with perfect truth and overwhelming complexity. The other sees a simplified dashboard. Food here, danger there, a safe path glowing forward. Only one survives long enough to leave descendants. Now bring that idea closer to your own body. Color does not live on the surface of objects. It lives inside you. Light arrives as wavelength and intensity. Your mind translates it into red or blue or gold. Sound arrives as pressure waves. Your mind turns it into the voice of someone you love, or the distant sigh of traffic at night. Already there is a gap between what exists and what is experienced. Then quantum mechanics steps forward like a cold wind through an open door. Niels Bohr once warned, "If quantum mechanics has not profoundly shocked you, you have not understood it." The shock is not only that particles behave like waves. It is that the act of measurement appears woven into what becomes real. In the double-slit experiment, a single electron sent one at a time creates an interference pattern, as if it passes through two openings at once. Add a detector to ask which path it took. The pattern changes. It behaves differently because you asked a different question. John Wheeler captured this strange humility. No phenomenon is a real phenomenon until it is an observed phenomenon. My now, not as mysticism, but as a description of what experiments continue to show. We want to believe the world is a book already written. That observation merely reads the page. Quantum results suggest something subtler, a story that tightens into one version when questioned in a particular way. So does the universe exist as a fully objective thing independent of observers? The honest answer is not a slogan. It is a tension. On one side, the universe is astonishingly reliable. It lets engineers build bridges. It lets surgeons repair hearts. On the other side, when we ask what the world is doing when nobody looks, the picture softens. Even conservative interpretations agree on this much. Properties are not labels waiting on objects. They arise through interaction. They are relational. That word sounds harmless until you feel what it implies. A universe made of relationships first, objects second. Consider the solidity of matter. It feels like the most reliable fact in your life. The chair supports you. The floor does not let you fall through. Yet atoms are mostly empty space. Electrons are probability clouds. When you press your hand against a wall, you are feeling electromagnetic fields refusing to overlap. The wall is solid in behavior, not in substance. Think of the image some see as blue and black, others as white and gold. The image did not change. Interpretation did. Experience is not a camera. It is a meaning maker. So a final distinction rises gently into view. There may be a difference between what exists and what is experienced. The universe may have structure independent of you, but the universe you live in is the one rendered through your biology, your history, your attention. Werner Heisenberg once said, "What we observe is not nature itself, but nature exposed to our method of questioning." Well, that does not make reality imaginary. It makes it participatory. So I leave you with a quiet question. When you say something is real, do you mean independent of you, or meaningful within experience? Leave your answer in the comments. Not to win an argument, but to light the way for others walking this path with you. What if the world you trust so completely is not the world as it truly is? We wake each morning convinced that what we see, hear, and touch is reality itself. The light spilling through the window feels honest. The sound of a passing car feels anchored in the street below. The warmth of a cup in your hands feels undeniable. And yet, beneath this calm certainty, science whispers a quieter, more unsettling possibility. The brain was never designed to reveal the truth of the world. It was designed to help you survive within it. Neuroscience has shown us that perception is not a window, but a construction. The brain does not receive reality and then understand it. It predicts, fills in, edits, and smooths. What reaches consciousness is already a finished draft, not the raw manuscript. As one cognitive scientist once said, "We do not see the world as it is, we see the world as we are." The eyes do not send pictures to the brain, they send electrical hints. The ears do not deliver sound itself, they deliver vibrations that the brain turns into meaning. Color, for example, does not exist out there in the universe. Light has no red or blue. It only has wavelength. Color is the brain's private translation, a poetic interpretation written in neural code. Sound is no different. Air moves. Pressure shifts. The music you hear is born only when the brain decides to listen. This realization leads to a deeper question. If our senses are constructing reality rather than revealing it, what might they be hiding? Evolution, after all, does not reward truth. It rewards survival. Theoretical biologist Richard Dawkins once noted that evolution favors good enough models, not perfect ones. Seeing the world accurately costs energy. Seeing it usefully saves lives. A brain that shows only what matters for action will always outcompete one obsessed with objective truth. Cognitive scientist Donald Hoffman takes this idea even further. He compares reality to a computer desktop. The blue folder on your screen is not the data itself. It is a symbol that helps you act without understanding the circuitry beneath. According to this view, space, time, objects, and even your body may be icons. Useful, intuitive, and deeply misleading. If this is true, then the solid table in front of you is not solid in the way you believe. It is mostly empty space. What you feel as hardness is electromagnetic resistance. What you feel as stability is an agreement between forces. The universe does not present itself honestly. It presents itself conveniently. And this brings us to the quiet tension at the heart of modern science. Are we explorers, uncovering reality, or navigators moving through a beautifully simplified map? Albert Einstein once warned that common sense is nothing more than the collection of prejudices acquired by age 18. Perhaps our deepest prejudice is believing that what feels real must be real. If our senses are filters, if our perceptions are interfaces, if evolution shaped us to survive rather than to know, then reality itself may be far stranger, quieter, and more abstract than anything we directly experience. And so the question lingers, gently but insistently. Are we seeing the universe as it is, or only as it allows us to survive? To answer that, we must step deeper, beyond perception, beyond sensation, and into the fragile boundary between reality and existence itself. If this sounds unsettling, it is because it gently dissolves one of our oldest assumptions, that the world is simply there, waiting to be perceived. In truth, perception may be closer to a negotiation than a revelation. Consider a simple example. A bat navigating the night sky does not see the world you see. It lives inside echoes. Its reality is sculpted from reflected sound, not light. To the bat, distance has a tone, shape has a delay, and motion sings back its position. The same physical world gives rise to radically different experiences, depending on the nervous system interpreting it. Even among humans, reality fractures quietly. Color blindness alters entire landscapes. Synesthesia blends sound into color and numbers into texture. Pain thresholds vary wildly from person to person. If reality were truly objective at the sensory level, these differences would not exist. What exists instead is a range of internal worlds, each convincing, each functional, none complete. This brings us to a humbling realization. We do not experience reality directly. We experience a biological guess. As neuroscientist David Eagleman has said, the brain lives in darkness, locked inside the skull, receiving only electrical signals. From these signals, it must infer the outside world. It has no access to truth, only to probability. Evolution shaped this inferential machine under relentless pressure. See the snake quickly, even if it is just a stick. Hear danger in the rustle, even if it is only the wind. False positives are cheap. False negatives are fatal. Accuracy, in this sense, becomes optional. Survival does not require truth. It requires speed, coherence, and usefulness. This is why the idea of reality as a user interface is so powerful. A computer desktop does not show you transistors, voltages, or binary code. It shows icons you can click. They are not honest. They are effective. According to this perspective, space may not be space as it truly is. Time may not flow as we feel it does. Objects may not be objects at all. They may be symbols evolved to guide action, not to reveal essence. Physics, strangely, seems to agree. At the smallest scales, the solid world dissolves into probabilities and fields. Particles are not tiny billiard balls. They are tendencies, described by mathematics, revealed only in interaction. As physicist Niels Bohr once remarked, physics is not about how nature is. It is about what we can say about nature. That distinction matters. The universe does not present itself naked. It presents itself through constraints, through measurement, through interaction, and the observer is never absent. Remove observation, and the equations remain silent. This does not mean reality is fake. It means reality is filtered, layered, translated. Like ancient stargazers projecting myths onto the night sky, we project meaning, structure, and solidity onto something far deeper and more abstract. The constellations were never really there, yet they guided navigation for millennia. Perhaps modern perception works the same way. A map, not the territory. A melody, not the instrument. When you look at the stars, you do not see nuclear fusion or space-time curvature. You see light arranged into beauty. When you touch a wall, you do not feel electromagnetic repulsion. You feel firmness. These experiences are not lies. They are translations. And like all translations, something essential is lost. So the question is not whether the brain deceives us. The question is why we ever assumed it would tell the truth. Maybe the universe is not meant to be seen clearly. Maybe it is meant to be lived within. If that is the case, then science becomes not a quest for absolute truth, but a gradual peeling back of the interface. A willingness to admit that what feels obvious may be deeply misleading. And in that humility, something profound emerges. A new kind of awe. Not the awe of certainty, but the awe of standing inside a mystery that does not owe us clarity. Because if reality is deeper than our senses, if existence is stranger than experience, then every moment of perception becomes a quiet miracle. Not because it reveals the universe as it is, but because it allows us to participate in it at all. And perhaps that is enough. What if the universe keeps its deepest secrets not behind distance, but behind the simple act of asking a question? What if a particle does not carry a definite story until the moment you demand one? For most of our lives, we move through a world that feels finished. A table is there, whether we look at it or not. A star burns in the dark, whether anyone names it. But quantum physics invites a gentler, more unsettling possibility. At the smallest scales, reality may behave less like a statue and more like a melody, not fully formed until it is played. The double-slit experiment is where this possibility becomes impossible to ignore. You take something that we call a particle an electron or a photon, and you send it toward a barrier with two narrow openings. You do it one particle at a time, slowly, patiently, as if you are listening for a faint sound in a silent room. If you do not try to find out which slit the particle goes through, the pattern that appears on the screen is not what common sense expects. It is an interference pattern, a set of bright and dark bands, like ripples on a pond crossing and cancelling and reinforcing each other. And the strange poetry of it is this. Each particle arrives as a single dot, but the accumulated pattern looks like a wave decided where the dots should land. Then you change only one thing. You place a detector to learn which slit the particle used. Now the interference disappears. The pattern becomes a simple spread, as if the particle behaved like a tiny bullet, choosing one path. In other words, when you ask the universe for the path, it gives you a universe with paths. When you do not ask, it gives you a universe with waves. This is not a metaphor for mystery. It is a measured difference in results. It is tempting to say the detector must have disturbed the particle. Surely the act of measuring kicked it, nudged it, forced it to behave differently. And sometimes, in everyday instruments, disturbance is real, but the deeper lesson is subtler than a shove. In quantum theory, measurement is not merely reading what is already written. Measurement is an interaction that creates a record, and a record is not a passive thing. A record is a physical imprint that ties the particle to the larger world, to the environment, to irreversible facts. The universe begins to feel like a stage where possibilities can dance freely until the moment the spotlight locks them into a single pose. Here is the first example to make this more human without losing truth. Imagine you are driving at night through thick fog. The road ahead exists, yes, but your experience of the road is created slice by slice as your headlights move forward. Farther ahead there is not a clear picture, only a haze of potential turns. The moment the beam touches a curve, the curve becomes definite for you, not because you invented the road, but because you forced one possibility to become actionable information. Quantum measurement can feel like that. Not the invention of the world, but the conversion of many allowed outcomes into one experienced outcome. The second example is quieter, almost intimate. Imagine a piano in a dark room. All the notes are possible, sleeping in the tension of strings. But the song is not present until a hand touches the keys. The instrument did not contain the melody as a finished object. It contained a space of structured possibilities. When you play a chord, the room fills with one reality and not another. Quantum systems, in a very careful sense, resemble that. They carry a structure of potential outcomes, and interaction selects which outcomes become part of the world's audible history. At this point, the mind tries to rescue itself with an older comfort. Maybe the particle really did go through one slit all along. Maybe it had a definite path, and we simply did not know it. Maybe there are hidden variables, secret settings in nature, that fix the outcome before we ever arrive. This idea is not foolish. It is the natural instinct of anyone who has ever trusted the solidity of a rock or the predictability of a sunrise. But physics did not stop at instinct. It asked nature directly, and nature answered with Bell's theorem. Bell showed that if reality is local and realistic in the classical sense, then certain correlations between entangled particles must remain within strict limits. Local means no influence travels faster than light. Realistic means properties exist before measurement. When experiments tested these limits with entangled photons, the limits were violated. Again and again, with increasingly careful setups, the universe behaved in a way that refuses to fit inside the old box. This is where Einstein's discomfort still echoes in the modern mind, because he famously called entanglement spooky action at a distance. How so? He was not being poetic. He was expressing a deep loyalty to the idea that the universe should not allow distant events to be stitched together without a local mechanism. So if hidden variables exist, they cannot be the simple local kind that preserves our familiar picture of separable objects carrying private properties. And if hidden variables do not exist at all, then we are forced to face a sharper question. What is the wave function? Is it merely a mathematical tool, like a weather forecast that describes our ignorance of tomorrow's wind? Or is it a real description of the system, a statement that the particle genuinely does not have a single definite value until interaction compels one? Here, the conversation becomes both scientific and philosophical, not because scientists are trying to escape into poetry, but because the experiments push language to its limits. If the wave function is only a tool, then perhaps reality is still classical underneath, and quantum mechanics is a clever map that never shows the territory. If the wave function is real, then the base layer of the world is not made of solid facts. It is made of structured possibilities, and the world of definite things is the world that emerges when those possibilities are forced to commit. This is why Niels Bohr's warning feels less like a slogan and more like a quiet diagnosis. If quantum mechanics hasn't profoundly shocked you, you haven't understood it. 1. Bohr was pointing to the gap between how we feel reality should behave and how the universe actually behaves when tested with precision. Not to glorify confusion, but to insist on humility. Because our intuition was trained on the middle world of stones and seasons, not on the subatomic realm where the rules of evidence reshape the meaning of existence. So, does observation create reality, or does it only reveal it? The safest answer is that observation is not mere looking, and reality is not mere furniture. Observation is physical coupling, the formation of correlations, the creation of records, and the loss of alternatives in practice. Reality, in the quantum sense, is what remains stable enough to be recorded and shared across the macroscopic world. When you measure, you do not necessarily summon the particle from nothingness, but you do force the system to choose a form that can leave a trace in the world you inhabit. The universe, under measurement, stops singing in chords and speaks in a single note. This does not mean the universe depends on human consciousness in a magical way. It means interaction is central. A detector, a screen, an atom in the air, a grain of dust, any environment that becomes entangled with the quantum system can play the role of measurement. Yet the mystery remains, not in the hardware, but in the meaning of definiteness itself. Why does the world of everyday experience feel so settled if the microscopic layer is so open? Why does the universe, at large scales, appear as a clean narrative rather than a fog of maybes? One answer is that the macroscopic world is built from countless interactions that constantly force outcomes into stable records. In that constant storm of contact, superpositions do not survive as visible experiences. They dissolve into the background, not because they were unreal, but because the information about alternatives becomes effectively inaccessible. The world becomes classical, the way a lake becomes smooth from a distance, even though up close it is always trembling with tiny waves. So when you ask, if there are no hidden variables, what is real, you arrive at a different definition of reality than the one we were taught in school. Real is not necessarily what exists with a complete set of private properties. Real may be what is consistent across interactions. Real may be what can be recorded and agreed upon when systems collide and exchange information. Real may be the shared surface of countless relationships rather than a secret core hidden inside objects. And that is where the educational value becomes almost tender. Quantum physics does not simply tell us the universe is strange. It teaches us how to hold uncertainty without panic. It teaches us that the desire for a single final picture may be more about our minds than about nature. It teaches us that the universe can be lawful without being intuitive, coherent without being classical, and profoundly real without conforming to our childhood assumptions. If you listen closely, the quantum world is not mocking us. It is inviting us to become more precise in how we speak about what exists. Not less human, but more careful. Not less curious, but more honest. So I will leave you with the question that quietly reshapes everything that comes after it. When you look at a particle and the universe answers with a definite outcome, are you witnessing a pre-written truth? Or are you watching reality settle, like starlight crystallizing on the surface of a still cosmic sea? What if the past is not a sealed vault, but a quiet room that can still hear echoes from the future? That single question sounds poetic, almost forbidden, yet it emerges from real experiments, real data, and the careful hands of physicists who never intended to unsettle our sense of time. From childhood, we are taught that the universe runs on order. First comes cause, then comes effect. The past solidifies. The future waits. Time, we are told, flows forward like a river that never turns back. But at the smallest scales of reality, that river begins to lose its banks. Quantum mechanics does not shout this disruption. It whispers it. And the whisper is enough to unravel centuries of certainty. Consider the delayed choice quantum eraser experiment. Not as a trick, not as science fiction, but as a disciplined question asked politely to nature. A particle is sent through an apparatus where it can behave like a wave, exploring multiple paths, or like a particle, choosing only one. If information about its path is available, the wave pattern disappears. If that information is erased, the wave returns. This alone is strange, yet the deeper disturbance comes later. The choice to erase or preserve that information is made after the particle has already been detected. And still, the results align as if the universe had been waiting for the question before deciding what the particle had done. It does not mean the future reaches backward and rewrites history like ink on wet paper. It means something far more unsettling, that the past, at the quantum level, may not be fully defined until information becomes settled. That events are not simply stored in time like files in an archive. They are resolved through interaction. John Wheeler captured this discomfort with quiet precision when he said, "No phenomenon is a real phenomenon until it is an observed phenomenon." This was not an invitation to mysticism. It was a warning that reality may be participatory rather than pre-written. To understand this more gently, imagine a book resting unopened on a table. The story exists as ink and paper, yet nothing is happening inside it. The characters are frozen. The choices are dormant. Only when the page is opened, does the story unfold in time. Quantum experiments suggest that physical reality behaves in a strangely similar way. Not because consciousness creates matter, but because interaction defines what counts as an event. This brings us naturally to causality. Is cause and effect a fundamental rule of the universe? Or is it a useful story that emerges when systems become large and warm and stable? Causality feels sacred because it protects predictability. It assures us that the universe keeps its promises. Yet quantum correlations appear without clear classical causes. Entangled particles respond as one system, regardless of distance. The order of explanation becomes dependent on how the experiment is arranged. Albert Einstein resisted this deeply, not because he lacked imagination, but because he valued coherence. His famous protest still echoes today when he said, "God does not play dice with the universe." End quote. And yet, the dice keep rolling, not chaotically, but consistently in ways that refuse our classical intuitions. Here is another image to make this clearer. Imagine reconstructing an accident using security cameras. Depending on which footage is recovered and when, the sequence of events appears different. In everyday life, we assume one version must be correct. In certain quantum scenarios, multiple reconstructions remain valid until information is fixed. Not because truth is subjective, but because properties do not exist independently of the context in which they are measured. From here, we drift naturally into the question of time itself. Does time truly flow? Or is flow merely how conscious systems experience change? You already know the answer emotionally. Grief stretches time. Joy compresses it. Memory folds it. Physics adds its own quiet provocation. Many fundamental equations do not care which direction time points. They work just as cleanly forward as backward. If the core laws are time-symmetric, then why does time feel directional? Why do we remember the past but not the future? Why do eggs break but never unbreak? The arrow of time, according to most physicists, is not a law. It is a statistical tendency. It arises from entropy, from the fact that disorder has vastly more possible arrangements than order. A perfectly arranged deck of cards is rare. A shuffled deck is inevitable. Time's arrow is not pushed forward. It is fallen into. And yet, entropy itself depends on how we describe the system, on what information we track, on what we ignore. Once again, observation returns to the center of the story. So can the future influence the past? The responsible answer is no, not in the cinematic sense, but also not no in the comforting classical sense. Quantum mechanics demands humility. It suggests that the clear boundary between past and future may be an emergent feature of our scale, not a fundamental architecture of reality. At the deepest level, the universe may resemble a tapestry rather than a timeline. Threads are correlations. Patterns are consistency. Before and after depend on how the weave is traced. There is quiet, educational value here. Not drama, not spectacle, but a lesson in how science actually behaves at the edge. It does not destroy reason. It refines it. It teaches us that reality is not obligated to match our metaphors. Perhaps the most meditative insight is this. We are not outside the universe looking in. We are participants within it. The past, the future, and the present may be different views of the same structure. So here is the question worth carrying with you. if time is not a flowing river, if causality is an emergent story, if the past is not fully written until information settles, then what exactly are you experiencing when you feel a moment pass? And if the universe waits to decide what happened until the right question is asked, what does that say about the nature of reality you have been living in all along? What if space is not the stage of reality at all? What if it is only the scenery, a convincing backdrop painted by rules we do not yet understand? And what if the true universe is not out there in 3 dimensions, but written somewhere else, on an edge we cannot point to, on a boundary we cannot touch? We grow up believing space is the container of everything, a vast, silent room where galaxies drift like lanterns in black water. Yet modern physics keeps returning to an unsettling suggestion. That space may be emergent, a consequence, a convenient illusion that appears when deeper ingredients arrange themselves in certain ways. As John Wheeler once put it, no phenomenon is a real phenomenon until it is an observed phenomenon. Not because reality is fragile like a dream, but because at the deepest level, reality may be relational, not made of objects sitting in space, but made of interactions that only look like objects. If that sounds poetic, black holes make it brutally concrete. A black hole is not merely a cosmic sinkhole. It is a question mark carved into the laws of nature, and the most shocking clue it offers is not its darkness. It is its accounting. Because when physicists began asking how much disorder a black hole contains, they expected the answer to scale with volume. More interior means more room for microstates. More room means more entropy. That is how ordinary systems behave. A bigger box can hold more possible arrangements than a smaller box. But black holes refuse this common sense. The entropy of a black hole scales with its surface area, not its volume. Not the inside, but the horizon. Not the depth, but the skin. It is as if the universe is whispering that the real bookkeeping of reality happens on boundaries, that the fundamental ledger is written on edges. This idea did not arrive as a metaphor. It emerged from hard mathematics and stubborn paradox. Throw a book into a fire and the information is not destroyed in principle. It is scrambled into heat, ash, and photons, but it remains encoded in the full physical state. Quantum theory insists that information is conserved. Yet if you throw that same book into a black hole, classical thinking says it is gone forever, erased. That would mean the universe breaks its own rules. So the black hole became a courtroom where the laws of physics were forced to testify against themselves. And the testimony was strange. In the end, the modern view that survived is that information is not truly destroyed by black holes. It is transformed. It becomes inaccessible in the simple way we imagine, but not annihilated from existence. This is why the information paradox mattered so much, because it was never only about black holes. It was about whether reality has a consistent memory, whether the universe is the kind of place where the past can be erased, or whether every event, no matter how hidden, leaves a trace written somewhere in the structure of the cosmos. Stephen Hawking once famously said, "Black holes ain't as black as they are painted." Dud. And behind that line is a deeper implication. A black hole is not a perfect grave. It is a transformation chamber, a place where the universe forces us to rethink what inside and outside even mean. Now, here is where the story becomes even more elegant and unsettling. If black hole entropy scales with area, it suggests a limit on how much information can be stored in a region of space. Not based on how much volume you have, but on how much boundary you can draw around it. In other words, the universe seems to behave as if the deepest description of a region is encoded on its surface. This is the seed of the holographic principle. The claim that the physics inside a volume can be fully represented by information living on the boundary of that volume. Like a three-dimensional world reconstructed from a two-dimensional script. Think of the hologram on a credit card. It looks three-dimensional. It has depth. It feels like it should have thickness. But the depth is an illusion produced by a flat pattern interacting with light and your perception. The entire 3D experience is encoded in a surface. The holographic principle suggests something similar, but at a cosmic scale. That what you call a three-dimensional universe might be the displayed image, and that the underlying reality could be a lower dimensional description, more fundamental than space itself. Here is the first example to make this feel less abstract. Imagine you are watching a live sports game on a flat screen. The players run. The ball arcs through the air. The stadium feels deep and spacious. But everything you are seeing is encoded on a two-dimensional surface. The depth is not in the screen. It is reconstructed in your mind from the information presented. Now translate that gently into physics. If the universe is holographic, then the depth of space might be like the depth of the stadium on your television. A real experience. A consistent experience, but not necessarily fundamental. It could be reconstructed from information on the edge. And not because space is fake, but because space might be the rendering, not the source. And the second example is even more intimate. Consider a shadow puppet show. On the wall, you see lions, mountains, dancers, whole dramas unfolding. The wall is flat. The images appear to move in a three-dimensional world of action. But the true causes are behind the screen, in a different space you cannot see directly, where hands and puppets create the pattern. If you spent your life studying only the shadows, you could measure their shapes and predict their motions with incredible accuracy. You might build a perfect physics of shadows. Honest. But you would still be studying the projection, not the puppet. The holographic idea invites a similar humility. Maybe our physics is astonishingly successful because it maps the shadows perfectly. Yet the deeper machinery could be encoded in a way that does not resemble space and time at all. Once you accept this possibility, other strange statements begin to feel less like science fiction and more like careful inference. If the universe can be described by information on a boundary, then three-dimensional space is not the primary fabric. It becomes an emergent pattern. And if space is emergent, the question, where is the universe, begins to wobble, because where assumes space is fundamental. It assumes a container. But what if there is no container, only relationships, only correlations, only a kind of cosmic accounting system that, when read from within, feels like distance and direction and location? So when you ask, are we living in the universe or reading from its edge, you are not just playing with language. You are touching the nerve of modern theoretical physics, because in holographic thinking, what you experience as being inside might be the internal perspective of a system whose full description lives elsewhere. Not elsewhere in the everyday sense. not across a gap you could travel, but elsewhere in the sense of a deeper representation, a more compressed truth, a description that is not written in the geometry of rooms and roads, but in the grammar of information. This is where the educational value becomes quietly profound. The universe may not be asking us to abandon reality. It may be asking us to refine what we mean by real. Real might not mean made of solid stuff in a vast container. Real might mean consistent relationships that can store information and preserve history. And real might mean patterns that survive transformation. A black hole then is not the end of the story. It is a test of whether the story can be erased. And the fact that physics keeps finding ways for information to persist suggests something almost spiritual in its restraint. Not mystical, not supernatural, but reverent, as if the universe does not allow itself to forget. And that brings us back to the opening question with a gentler clarity. Is space the foundation of reality? Or is it the appearance of something deeper? Black holes, with their area-bound entropy, hint that the universe keeps its secrets on surfaces. The holographic principle hints that the world we walk through may be a projection of an underlying informational structure. And the information question hints that existence is not a pile of objects. It is a continuity of encoded relationships. So the next time you look up at the night sky, try a different imagination. Not stars scattered in a container of space, but a shimmering display, coherent and lawful, rising from an invisible script. A script written on an edge you will never reach by traveling, only by understanding. And if that is true, then the most haunting question is not whether we are small. It is whether we have been mistaking the screen for the source. If the universe is a hologram, then what is the boundary made of? And who, or what, is doing the reading? What if the smallest pieces of reality are not things at all? What if, when you chase matter down to its final brick, your hand closes on empty air, and yet the world still feels solid? For centuries we pictured the universe as a cabinet filled with objects. Tiny beads called particles, each with its own private identity, each a miniature stone tumbling through space. But modern physics asks us to trade that comforting picture for something stranger and, in a way, more beautiful. Because the deeper we look, the more it seems that a so-called particle is not a separate object, but a momentary note in a cosmic instrument. A ripple, a localized shiver, a brief crest in an ocean that never stops moving. Richard Feynman once offered a line that still lands like a quiet thunderclap. "Everything is made of atoms," he said, and then he spent his life showing us that even atoms are mostly emptiness, held together by rules that feel more like choreography than like bricks and mortar. And if we follow that choreography one step further, we arrive at the idea that matter is not made of little pellets at all. Matter is what a field looks like when it vibrates in the right way. A field is not a substance you can scoop up. It is not a mist or a fluid, although those metaphors help at first. A field is more like a presence that can take on patterns. It stretches everywhere, even through places we call empty. And when it is disturbed, it can ring. That ringing shows up to us as what we call a particle, a small packet of energy, a discrete click in a detector, a dot on a screen. So the particle is not a tiny object traveling through a void. It is an event, a localized excitation, a temporary knot in something continuous. This is why the question, Our fundamental particles, separate objects, starts to soften at the edges. Because if an electron is an excitation of the electron field, then every electron is not a different marble. Every electron is the same pattern appearing in different places, like the same musical note played again and again on different pianos. That is why electrons are perfectly identical, not merely similar, but truly indistinguishable in every measurable way. It is not because the universe is mass-producing them with perfect quality control. It is because the electron is not a manufactured object. It is the field's signature, the one and only way the electron field can spark when it is excited. And that takes us into a more meditative thought. When you look at a crowd, you see faces, you see individuals. When physics looks at electrons, it sees something more like a single melody, repeating across the cosmos. The sameness is not a coincidence. It is the deep symmetry of nature, a kind of quiet lawfulness that runs beneath the noise of daily experience. But now we should ask something that sounds simple, yet changes everything. If fields are everywhere, what about the vacuum? Is empty space truly empty, or is it only empty in the way a silent room is empty, while still filled with air, temperature, tension, and the possibility of sound? Here, the universe becomes almost poetic in its refusal to be nothing. Even the lowest energy state of a quantum field, the state we call the vacuum, is not perfectly still. It trembles. It flickers with fluctuations that cannot be removed, not because our instruments are weak, but because uncertainty is built into the rules. So, the vacuum is not a blank page. It is a page already humming with invisible ink. This is where the Casimir effect enters, like a gentle demonstration you can almost feel in your fingertips. Imagine two extremely smooth metal plates, placed very close together, with a tiny gap between them, and the space around them, otherwise evacuated as much as possible. Classically, you would expect nothing to happen. No air, no wind, no pressure difference, no reason for motion. And yet, in the real quantum world, the plates experience an attraction, a small, measurable force. Not because something pushes them from the outside in the ordinary sense, but because the vacuum itself is not equally free to fluctuate everywhere. Between the plates, only certain wave patterns are allowed. Outside, more patterns are allowed. That imbalance produces a net effect, a pressure of possibility, a subtle persuasion that nudges the plates together. The lesson is almost unsettling. Nothing has structure. Empty has consequences. And now, gently, we circle back to the feeling that started this entire mystery. Why does the world feel solid if atoms are mostly empty space? If you magnify a single atom to the size of a cathedral, the nucleus would be a tiny speck at the center, and the electrons would not be little planets, but probability patterns, a spread of potential presence. Most of that cathedral would be empty. So, why does your hand not pass through the wall? The answer is not that matter is packed tight. The answer is that fields resist overlap in specific ways. When you press your hand against a table, you are not colliding hard pellets of substance. You are bringing the electromagnetic field patterns of your atoms close to the electromagnetic field patterns of the table's atoms. And those patterns do not simply merge. They respond. They repel. They enforce the rules that keep structures stable. Solidity, then, is not the presence of dense stuff. It is the insistence of interaction. It is a feeling produced by forces, by field behavior, by the universe saying, in its quiet mathematical language, not there, not the same place, not that configuration. Here is a second example that makes the idea more intimate. Think of a crowded elevator. The people inside are mostly empty space too, made of atoms with vast gaps inside them, and yet no one can occupy the exact same spot comfortably. Not because bodies are made of solid stone, but because the patterns that define a body include boundaries of interaction. When those boundaries meet, the rules become tactile. The sensation of solid is the body translating invisible constraints into a simple message you can live by. Stop. There is something here. Albert Einstein left us a sentence that feels almost like a lantern in this fog. Reality is merely an illusion, albeit a very persistent one. He did not mean that nothing exists, or that life is a dream to be dismissed. He meant that the picture in our minds, the naive sense of objects as separate little islands of substance, may be an approximation that works for daily life while hiding a deeper structure. And in the modern view, that deeper structure is not built from things, but from relationships, from fields and excitations, from probabilities and constraints, from the restless activity of a vacuum that never quite sits still. So when we ask what matter is, we may be asking the wrong kind of question. Matter is not a substance you can point to beneath everything else. Matter is a behavior, a stable pattern in the underlying fields, a long-lived rhythm that repeats so reliably it becomes a chair, a tree, a human face, a memory. And if that is true, then the universe is not a warehouse of objects. It is closer to a vast symphony of interacting fields, where what we call particles are the notes, and what we call emptiness is the silence that is never truly silent. Which leaves us with a final, lingering thought. If the vacuum is alive with possibility, and if solidity is a sensation born from invisible rules, then perhaps the deepest reality is not what we can hold. Perhaps it is what holds us. And the next time you rest your hand on a table and feel its firm resistance, you might wonder, are you touching matter? Or are you touching the universe's way of saying that even nothing is not nothing at all? What if space is not a stage that exists before the play? What if it is born only when the actors recognize each other? When two things become related, when information passes between them, when the universe decides that here and there should mean something at all. We grow up imagining space as a silent container, a vast, empty hall where stars are hung like lanterns and planets drift like dust. But modern physics keeps whispering a different story. A story in which space might be a consequence, not a cause. Not the flaw beneath reality, but the shadow cast by relationships. And if that is true, then the most unsettling question is not how big the universe is. It is whether the universe has a where in the first place. Albert Einstein once admitted, time and space are modes by which we think, and not conditions in which we live. And that line, quietly poetic, feels less like philosophy and more like a warning label now. Because the deeper we look, the more space behaves like something that can be stitched together, torn apart, and even replaced by something more abstract. In loop quantum gravity, one of the bold attempts to unify gravity with quantum theory, space is not smooth like an infinite sheet of silk. It is more like a woven fabric, made of tiny loops of quantum geometry. Not loops floating inside space, but loops that are space. At the smallest scales, the idea goes, The universe is built from discrete units of area and volume, like grains of sand that no microscope can ever fully turn into a continuous beach. In this picture, you do not start with a cosmic grid and place objects into it. You start with a network of connections, a web of relations, and what we call distance emerges from how tightly those connections are tied. Close is not a measurement on a ruler. Close is a kind of intimacy in the underlying structure. Now pause and consider the implications. If space is a web of relations, then position is not a thing you own. It is a thing you earn through interaction. A location would not be an address written into the universe. It would be a statement like, I am related to this, and this, and this. Without that relational context, the word here becomes as empty as a name spoken into a void with no ears to hear it. This is where the question becomes almost haunting. Does location exist if there are no relationships? If nothing can interact with anything else, if no information can be exchanged, then what would it even mean to say something is somewhere? 1. It might be like trying to define left and right in a world with no reference point, or like insisting on a melody when no note has ever been played. The universe, in that sense, may not come with coordinates. It may come with connections. Here is a simple image to make this tangible. Imagine a town at night seen from above. You might think the town is defined by its streets and geography. But if you turn off every light, every signal, every phone, every road, every bridge, then the town becomes a meaningless label. What actually makes the town real to its inhabitants is the network of relationships. The roads that connect homes, the conversations that travel, the supply lines that feed it, the maps that guide it. In the relational view, space is less like the land beneath the town and more like the pattern of connection that makes the town a coherent thing. A second example comes from something we all carry: a smartphone. On its screen you see icons separated by distances. You swipe left, you swipe right, you feel as though you are moving through a space. But inside the device there is no left or right. There are only electrical states and relationships between circuits. The space you experience is a user-friendly rendering of deeper relationships you do not directly perceive. Some physicists suspect our universe might work in a similar way. Not as a cheap simulation, not as a trick, but as a reality whose deepest layer is not spatial at all, and whose space is a kind of emergent interface. And then we reach time, the more intimate mystery. Because if space can emerge from relationships, time might emerge from change in relationships. Or more precisely, from how information becomes organized and irreversible. At the level of fundamental laws, many equations do not care whether time runs forward or backward. And yet our lives do. We remember the past, not the future. We break a glass and never watch it leap back into our hand. We age. We mourn. So where does this arrow come from? Some ideas suggest that time, as we feel it, may arise from entanglement and entropy. Entanglement is the eerie quantum linkage that makes separated systems behave like parts of one hidden whole. Entropy is the measure of how many possible internal arrangements a system could have, given what you can know about it. When entropy increases, information about precise details becomes effectively lost to the larger world, and a direction appears. Not because the universe has a clock built into its bones, but because the universe has a tendency to move towards states that can be described in more ways than before. Time, in this view, is not a river flowing through reality. It is the footprint left behind by information becoming more dispersed, more scrambled, more out of reach. This is where the Wheeler-DeWitt equation enters like a cold wind through a doorway. It is a proposed equation for the universe as a whole in quantum gravity, and famously, it contains no time variable in the way we expect. That does not mean change is an illusion. It means that at the deepest level, the universe may be describable as a complete structure, a total configuration, without needing an external ticking parameter. If you are used to imagining reality as a film playing frame by frame, this suggests something stranger. That the entire film might exist as a whole, and what you call time is the way a conscious system experiences correlations within that whole. Carlo Rovelli, one of the leading voices in this area, put it with disarming simplicity. Time is not fundamental. How? When someone like that says it, you can hear the careful humility behind the words. Not an announcement of certainty, but a recognition that our instincts might be adapted to survival, not to the architecture of the cosmos. And yet none of this is meant to pull the rug out from under your feet. It is meant to refine what your feet are standing on. Because the educational value here is not the shock of strange ideas. It is the discipline of letting reality be more subtle than the pictures in our minds. We once thought the Earth was the center, then we learned it was not. We once thought space and time were absolute, then we learned they bend. Now we are learning they may not even be the starting point. So when you look at the night sky, and you feel the calm of distances, the comfort of out there, consider this softer possibility. That the vastness you see may be a translation, a beautiful rendering of relationships too deep for our senses to hold directly, and that your life, your awareness, your moment of attention right now might not be happening inside a pre-existing container called space and time. It might be the universe forming a local pocket of coherence, where relations become geometry and change becomes duration. If space is born from connection, then separation is not the default. If time is born from entropy, then the present is not a point on a line, but a way a mind navigates a shifting web of information. And that leads to a quiet, meditative question that lingers like starlight on the edge of sleep. If space and time are not the stage, but the story, then what is the storyteller? What if the universe is not a machine made of matter? What if it is a calculation that only looks like matter? And what if every star you have ever loved is simply the luminous output of deeper rules you cannot see? John Archibald Wheeler once compressed an entire revolution into 3 words. It from bit. End. He meant that everything we call real may arise from information, from yes and no, from the smallest possible distinctions that can be registered by nature. If that sounds abstract, hold it gently for a moment, like a stone warmed by the hand. Because modern physics keeps leading us back to the same unsettling threshold, where substance dissolves into structure. We are used to picturing reality as continuous, like a smooth ocean with no pixels. Yet at the smallest scales we can meaningfully describe, nature behaves as if it has steps, packets, quanta. Energy arrives in lumps. Angular momentum comes in allowed values. Even the vacuum, which once sounded like perfect emptiness, behaves like a restless stage where fields fluctuate and bookkeeping becomes physical consequence. This does not prove the universe is digital, in the way your laptop is digital. But it does whisper a possibility that the deepest layer may be discrete, not because someone built it, but because consistency itself may require a smallest unit of change. Here is one way to feel it without equations. Imagine you zoom into a photograph on your phone. At first you see a face, then pores and hairs. Then the texture becomes blocks of color. There is no betrayal in that revelation. The image is still the image. It simply has a resolution, a limit beyond which the smoothness was always an illusion of distance. Some physicists wonder whether space-time may be similar. Not fake, not a trick, but rendered, emergent, appearing continuous only because we live at the scale where the pixels blur into serenity. Now step from pixels to information, because black holes force that step upon us. A black hole is not merely a gravitational monster. It is an argument carved into the universe, insisting that information matters as much as mass and motion. When we ask how much information can be stored in a region of space, black hole physics suggests a shocking answer, that the maximum is tied to surface area, not volume. It is as if reality keeps its ledger on the boundary, as if the universe prefers edges to interiors. This is one of the doorways into the holographic principle, the idea that a world with depth might be fully described by a description written on a lower dimensional screen. If that is even approximately true, then where becomes less fundamental than how much information and how tightly entangled. Space begins to resemble a map drawn by correlations, not a container waiting politely in the background. And once you start speaking the language of information, the word code arrives almost by itself. Not code as in lines written by a programmer, but code as in rule, constraint, transformation, the grammar of what can follow from what. Physical law is strangely compact. A small set of principles gives rise to an ocean of phenomena. That compression is exactly what good code does. It does not create complexity by adding more words. It creates complexity by letting a few rules iterate, again and again, until patterns bloom. This is why Stephen Wolfram's proposal keeps reappearing in serious conversation. He suggests that the universe might be the evolution of simple rewriting rules, generating a growing network of relationships from which we later extract our familiar notions of particles, space, and time. Is he right? No one can responsibly declare victory here. But the value of the idea is that it dares to ask whether physics is describing reality's behavior from the outside, or whether it is catching reality in the act of computing itself from the inside. In that view, the universe is not running equations. It is the equation unfolding. To make that intuitive, consider a second example. Think of a simple game with a tiny rule book. Chess has a few rules, yet produces more distinct games than any human could play in a lifetime. The rulebook is small, but the space of outcomes is vast. Now imagine nature as a rulebook whose iterations are not entertainment, but existence. Stars, rivers, neurons, and memories become stable motifs, like recurring strategies in an endless game, not because they were planned, but because the rules allow them to persist. At this point, the conversation touches mathematics, and the air becomes almost reverent. Because mathematics does not feel like a human invention in the way a hammer is an invention. It feels like something we discover, like a coastline we keep mapping, only to realize it was there long before we arrived. Galileo famously wrote, Mathematics is the language in which God has written the universe. You can read that line in a spiritual register or in a purely poetic one. Either way, it captures the strange intimacy between mind and cosmos, between symbol and star. But it also raises the sharper question, does mathematics merely describe the universe, or is the universe itself a mathematical structure? Max Tegmark and others have argued, cautiously but boldly, that physical reality might be identical to a consistent mathematical object. If that is true, then the difference between map and territory collapses. The map is the territory, and we are patterns inside it, awake enough to notice the symmetry. Still, even if the universe behaves like computation, we should be careful with the word digital. End quote. Quantization alone does not prove a cosmic computer. Information bounds do not automatically mean a memory chip. And code can be a metaphor that flatters our era, because we live among screens and software and cannot help seeing the cosmos through that lens. Yet the deeper educational value remains. Physics is teaching us to trade the old instinct of substance for the newer instinct of relationship. To ask not only what something is, but what it can know, what it can store, what it can exchange, and how those exchanges carve the world we experience. So perhaps the gentlest conclusion is this: the universe may not be a computer in the way we build computers, but it may be computational in the way it evolves, conserving information, compressing law, and generating form through iterative structure. And if mathematics is the skeleton of that structure, then our minds, which can think mathematically, are not strangers here. They are resonances, tuned to the same deep grammar, which leaves one final, quiet question hanging in the dark like a lantern. If reality is made of rules and information, then, when you look up at the night sky and feel meaning rise in your chest, is that meaning something the universe contains? Or is it something the universe makes possible by giving you just enough order to become aware? What if the universe does not become real until it is noticed? And what if the act of noticing is not a passive glance, but the final brushstroke that paints the world into being? In everyday life, reality feels obedient. A table stays a table whether you look at it or not. A star burns whether your eyes are open or closed. But when we descend into the quantum scale, the ground turns strangely soft, like walking on fog that remembers your footsteps. We meet the wave function, a mathematical whisper describing not what is, but what could be. And then comes the jolt. When a measurement happens, the whisper seems to harden into a single fact. So the haunting question is simple to ask and brutally hard to settle. What truly causes that collapse into one outcome? Some physicists treat collapse as a real physical event, a kind of cosmic decision. Others suspect it is not a collapse at all, but a shift in what an observer can know. Decoherence, for example, suggests that the quantum world does not choose in a mystical way, but becomes entangled with its environment until the delicate interference is effectively washed out. In that view, the universe does not need a conscious mind to become classical. It needs interaction, noise, and the irreversible spreading of information into the surrounding world. Yet even this elegant idea leaves a lingering ache. Decoherence can explain why possibilities stop interfering. It does not fully explain why you experience one definite outcome, here, now, instead of all outcomes at once. That leads to the next question, the one people are often afraid to say out loud. Does observation require consciousness, or is a measuring device enough? A camera, a detector, a grain of dust, do they count as witnesses? Or does reality wait for awareness itself, the quiet inner light that says, "I see"? Eugene Wigner once pressed directly on this sore spot, suggesting consciousness might be essential to the story. Not as magic, not as wishful thinking, but as the missing bridge between equations and experience. Whether or not one agrees with him, the discomfort he pointed to remains. Physics can predict the statistics with astonishing precision, but the leap from probability to lived fact still feels like a locked door. Here is a first example that makes the issue easy to picture. Imagine a simple double-slit experiment. When no path information is recorded, electrons form an interference pattern, as if each one behaves like a wave exploring multiple routes. When a detector is placed to learn which slit the electron passes through, the interference vanishes, and the electron behaves like a particle choosing one path. It is as if the world changes costume when you ask a sharper question. Now ask yourself what detector really means. Is it the metal and wiring alone? Or is it the fact that the information could, in principle, become known to someone? Wigner's friend sharpens this into a philosophical blade. Picture a friend inside a sealed lab measuring a quantum system. From your friend's perspective, the moment the result appears, reality becomes definite. But from your perspective outside the lab, if you treat the whole lab quantum mechanically, your friend and the measurement could remain in a superposition, a blurred story not yet settled. So whose reality is real? Did collapse happen when your friend saw the result? Or only when you opened the door and learned it? The thought experiment is unsettling because it threatens the idea of one shared world. It hints that facts might be local, stitched to observers, rather than floating in a universal archive. That brings us to a deeper possibility entertained by relational approaches. Maybe there is no single, God's eye version of reality. Maybe there are only relationships, events, interactions, and the truths they generate between systems. In such a view, asking for a single global account might be like demanding one definitive description of a melody without any listener, any instrument, any air to carry the sound. Reality becomes less like a stone and more like a conversation. Not because it is subjective fantasy, but because the very meaning of state may be inseparable from who is interacting with whom. John Wheeler captured the mood with a line that still echoes through modern debates. No phenomenon is a real phenomenon until it is an observed phenomenon. 5. Take that sentence gently, not as a final verdict, but as a warning flare. It reminds us that physics is not merely describing objects. It is describing the outcomes of encounters. And encounters always have two sides. Here is a second example, grounded in ordinary life. Imagine a motion sensor camera in a forest at night. A deer passes, and the camera records it. Days later, you watch the footage. Did the deer become real only when you viewed it? Most of us would say no, the deer was there regardless. But quantum theory tempts a stranger question at smaller scales. If the camera's record is itself a physical interaction that irreversibly spreads information into the environment, then perhaps reality became definite at the moment of recording. Yet if you insist that definiteness requires an experienced fact, then perhaps the story is not complete until someone knows. The forest is the same, and yet the logic of what counts as a witness shifts depending on which interpretation you lean toward. Now the thread pulls tighter, and it leads us out beyond physics into the last philosophical horizon. If space is not fundamental, if time is not fundamental, if matter is not a collection of solid things but a dance of fields and probabilities, then what is the universe? Perhaps it is not a container at all. Perhaps it is a pattern of relations, a web of constraints and correlations that only looks like a vast stage when you stand inside it and call the view space. 1. Perhaps reality is not a noun, but a verb. Not a thing that sits there, complete, but a process that happens, moment by moment, whenever systems meet and exchange information. And where does meaning live in such a world? The equations may be breathtakingly beautiful, but beauty is not the same as purpose. The cosmos may be structured, but structure is not automatically a message. Meaning might not be etched into the bones of the universe the way we secretly hope. Meaning may arise in the one place it undeniably appears, within conscious experience. Not as a cheap comfort, but as a responsibility. If meaning is something minds generate, then minds are not trivial accidents. They are the places where the universe learns to reflect on itself. Then comes the quietest question of all. Could nothing be the most stable baseline? Not empty space, which is already full of laws and fluctuations, but a deeper nothing, where even the idea of a rule has no footing. And if so, why is there something rather than nothing? We may never own a final answer, but the search itself teaches a kind of intellectual humility that is rare and precious. Because every time we try to pin reality down as an object, it slips into relationship. Every time we demand a foundation, we find another layer of description. It is as if existence is less a monument and more a ripple, sustained by coherence, by interaction, by the delicate persistence of pattern. So are we living in a universe, or inside a question that keeps rewriting itself? If the universe does not exist the way we assumed, then what are we doing here? Perhaps we are not spectators in a finished world. Perhaps we are participants in an unfolding one. And perhaps the most honest posture is neither fear nor arrogance, but attentive wonder. Because in the end, the strangest possibility is also the most intimate. That reality is not something you merely find. It is something that happens, again and again, at the edge where observation meets the observed.